Good morning. I'm Guo Yuan Lien from RIKEN X, and I'm working with Takemasa Mills on the high-resolution radar data assimilation using the LETKF. So in this talk, I'm going to discuss some issues related to the thinning and the localization of the assimilation of the dense observation data, such as this very dense radar data. So in recent years, when we have bigger and bigger observation data from the advanced remote sensing platform, like the high-resolution radar or a high-resolution satellite. So if to effectively assimilate such dense data in the ensemble common filter, we know we need to do the thinning and the covariance localization, and they need to be carefully treated. But there are also problems related to this. So first, it's a non-trivial effort to tune this. So if we don't have some adaptive method, it's maybe just you need to tune it carefully. And also, maybe the most importantly, thinning obviously decreases the resolution of the observation data. So which seems to be contradictory to our pursuit of the high-resolution observation data and the high-resolution models. So is there some alternative ways to do this? So before describing the alternative way, first we think about what's the reason of the thinning and the covariance localization in the ensemble common filter for this dense observation. So there are several different reasons. For thinning, it may be used to deal with the observation error correlation or the representativeness errors. And for localization, maybe the most obvious reason is to deal with the sampling error with a limited ensemble size. However, there are also some reasons which is shared by both thinning and localization. So one is to reduce the observation numbers compared to the ensemble size or the degree of freedom of the analysis. And this limitation is actually discussed in several literatures. And also, this is also discussed by the talk by Daisuke Hota in his talk on Tuesday. So actually, it is concluded that if we use ensemble common filter method, then if you estimate too many observations compared to your ensemble size, then there are some bad effects, like you will get too smooth analysis field, and also you will get too small ensemble spread, which is not good for the data assimilation. And another important reason is just for the computational cost, because you have too many data, and it's not, the computation become very expensive. So with the very dense observation data, actually we think these two reasons become much more important, because we know that our ensemble size can never beat the number of observations, and also the computation cost is very expensive. So actually, there are alternative way to do this kind of localization and thinning. And so this is in the LETKF framework. So in the LETKF, because we analyze each grid independently, so actually we can limit the number of observations used in each grid. So actually, I call this observation number limit in the LETKF. And this method is actually, to my knowledge, it has been implemented in at least two LETKF systems in the operational center. So like in the ECMWF global model, they implemented this, and they implement the number of they limit the number of observations used at each grid point for each different report type and variables. And also in the German weather surface regional model, they keep a constant of the effective number of the observations used at each grid point. So there are some differences in the implementation, but the basic ideas are the same. So what is the the criterion to choose those limited number of observations for each grid? Is simply just the distance to the analyzed grid. So observations spatially closest to the analyzed grid are selected. So what's the advantage of this observation number limit? So actually, with the ECMWF global model, they actually observed significant improvements of the analysis and the forecast by assimilate even fewer data, and also it also saves like computational time. So this is not a new method, but we implement this and test this technique in our regional data assimilation system, assimilate very dense observation data at a very high model resolution. So I think like in this very dense observation and very high resolution situation, this consideration of observation number become more important. So we really like to see the impact of this method. So this is just a schematic of how this observation number limit works compared to the traditional thinning method. So assuming we have this kind of distribution of the observation, we have more dense observation here. So if you do the thinning, it means you first define the thinning mesh like this, and then you pick up only one observation per thinning grid. So we pick up only the red observations, and we discard all of the other gray observations before doing the data assimilation. So in the LETKF, we define some localization radius. So like for these three grid points, A and B and C, the observations assimilated for these three grids are the observations marked by this cross sign and the circle sign and the plus sign, circle sign, and the cross sign respectively. Yeah, so actually there are some observations are used in different. The observations are used in different grid. So if we apply the observation number limit, so what is the observation picked up by this method? So actually we input the original observation data. We don't think the data before, but in the LETKF, like they pick up the 10 closest observations in these three grid points. So we actually pick up the observation like this. So in the dense observation area, the real localization cutoff radius become smaller, and in the sparse area, it's become larger. So we know there are some differences of this method compared to the thin method. The first, this method doesn't sacrifice the resolution of the observation data. So it actually uses the original high resolution data. And the second, this method pick up a more independent set of observation by each grid. So let's briefly describe our experimental design. So we use a regional weather prediction model called the scale model, also developed in this institute by another group. And we use the LETKF data assimilation, and we estimate the phase array weather radar, which is advanced radar which can observe more high spatial and temporal resolution data. It observed about 100 times more data than the conventional radar. So this is the design of the domain. So we use this multiple nested system to propagate the large-scale environmental condition to this small, very high-resolution inner domain. So in the innermost domain, we run model at a 250-meter resolution and estimate both the reflectivity data and the radial velocity data at 30-second update cycle. So just to look at how dense our observation data are. So the original data is in the polar coordinate with 600 radial points and 300 azimuthal angles and 98 elevation angles. So yeah, this is the original data. And then we first perform the superobing of this data to the 250-meter mesh, which is the model resolution. This is mainly to deal with the representativeness errors. So we first superob to this for all of the experiments. So this animation shows the result of the superobing. So actually, in the area close to the radar center, it's almost every 200-meter grid has one observation. But in the farther area, there are some gaps here. But in all, the density is still very high. And so the number of superobing data is like this much. So for reflectivity observation, we have about 3 million. And for radial velocity, we have about 170,000 observations every 30 seconds. And the data really assimilated into the model is like fewer for the reflectivity, much fewer for the reflectivity, mostly because that we reject the data when the model and the observation are clear sky. So we don't do anything in this case. But for the radial velocity data, we assimilate almost all data. So we set up this this experimental design. So we conduct several sets of experiments. The first set is with the 100 ensemble members, and we tested several different number of the different number limits, and also the unlimited, which means the original LETKF. And we also conduct the experiment with fewer ensemble members, 25 ensemble members, and we also compared the result with the traditional thinning method. So this is just to have an idea of how is the model analysis and forecast look like in one experiment. So the right panel is observation, and the left panel is the model 10-minute analysis followed by 30-minute forecast. So when the background is gray, it's analysis, and when background change to purple color, is 30-minute forecast. So basically, you just see in the analysis, because we assimilate this data, so it becomes very similar, and in the forecast, they become more and more different. So look at some objective score. So here we calculate the threat score and the bias score verified against the reflectivity observations. So this is for the experiment without the observation number limiter or the original LETKF. So if we employ the observation number limit, this is the result. So actually, with this observation number limit, we actually can improve the result, and also it's most significant in the first few in the early period of the forecast, and the 100 number limit leads to the best results. And for the bias, they are almost similar, but except for the experiment with the fewest limit. And this is the result with the 25 members. Basically, we observe a similar trend. So this number limit can improve the result, especially in the the early forecast time. And so here we use this figure to summarize this result. So this figure shows the mean 5 minutes and 30 minutes forecast threat score. So in the red is a 100-member result, and the blue is a 25-member result. So basically, we see some optimum value. There are some optimum value of the number limit for each different ensemble size. So and we find that the optimum value of this number limit is roughly proportional to the ensemble size. And also, if we compare with the experiment with the number limiter and without the number limiter, we see that in particular in the first 5-minute forecast, applying this number limiter is very beneficial compared to assimilate all of the observation data. But if you average for the entire 30-minute forecast, it's not much better, but still some benefit. And so let's look at what this observation number limit impact, what it is doing with the analysis. So this figure shows the number of observations assimilated into our system in one cycle. So if you don't use the number limit, actually we can assimilate this number of observations for one grid point. This is a log scale. So we actually assimilate more than 100,000 observations in this region. And if you apply the number limit, you basically just cut these numbers to this maximum number limit. And this is the real localization cutoff radius with the implement of these number limits. So if in the original LETKF, we use 4 kilometer localization length scale, which equal to about 15 kilometer cutoff radius. But if you implement this, then if you choose a smallest number limiter, you actually change adaptively change the localization radius to a very small, very small distance. Like in this 25 number limiter, it changed to only about 0.5 kilometer, and this it changed to about 0.9 kilometer. So actually, localization radius is adaptive to the observation density in this method, and we also look at the increments in the first cycle of the reflectivity by this in this experiment, and we actually surprisingly find that they are pretty similar, even if we only assimilate a small number of observations. So we have other additional experiments using the traditional thinning method. So this is the observation number assimilated after we use the thinning. So here I just want to say that if you want to reduce your observation number similar to this, like the optimum observation numbers in this number limited experiment, you need to use a very strong thinning, like you thin by every 16 by 16 grid point of 4 kilometer. Then only if you do this strong thinning, you can get this small this number comparable to ensemble size. But the increment become very different, in this case. So actually, by doing this strong thing, you actually you get much small increment, and not like this. So this is the result of threat score of compare with this number limit experiment and the thinning experiment. So actually, this, if you thin 4 by 4 grid point, it's actually similar to the original LETKF, but it's worse than the number limit. And if you thin strongly thin like this, you actually get even worse result. And finally, this is the computational time of this method. So I just want to show, it can reduce the computational time. And so finally, there are some discussions, and this number limit. So we have some like theoretically we cannot assimilate too many observations in the ensemble common filter framework, especially in the LETKF. And so we think that in the situation of the assimilated dense mesoscale observation data, this may be the dominant reason for thinning. So compared to the other reason like representative error or observation error correlation, and it may also an important reason for localization. And so if we can only assimilate a limited number of observations, we should choose the most important ones. And the observation closest to the analyzed grid may be a good candidate. And the increment change only very little. And the traditional thinning method may over-thin the data, lose the small scale information. And I was giving some, So we would like to suggest some strategy for simulating dense observation data with the LETKF. So we know there are observation error correlation and representative error issue we need to deal with. So first, we still need to mitigate this issue by some method like thinning, or you can actually solve it in a more fundamental way, like considering the 4R matrix. But if you do thinning, actually we don't need to do too strong thinning. And then after that, we assimilate with the observation number limit with the limit with is about a few times of the ensemble size. So this, so I will stop here, and thank you very much for attention.